All right, question 6, the question on driving the direction of elimination. So, I wanted you to see actual data on what base size does. So in this case, with ethoxide, a relatively small base, no real steric problems there, we're looking at an okay distribution between the more and less substituted alkenes, the left and the right one. Or if you like the terminologies Zaitsev and Hoffman, I don't like those terms, so I don't use them. I think they encourage memorization. So more substituted, less substituted, makes you think about why that would happen and what it means. So those are the terms I use. But in the other case, with the T-butyl group, we're seeing an opposite. We're seeing that completely flip around, because getting to the more substituted hydrogen that would lead to the more substituted carbon is more difficult. So basically the T-butyl group is taking a hydrogen from here preferentially, whereas the ethoxide is taking a hydrogen from here preferentially. All about size. So, how does it work? I didn't ask you to draw the T-butyl one. It's the same mechanism either way. It's just a matter of whether the size is a problem or not. So we're not really going to consider that for the mechanism. But the reason this happens is size. If I wanted to drive this further, I'd get an even bigger base. T-butoxide is not the end of the line. There are things that are ludicrously large compared to that I could use and probably get that right product up into the 80s or 90s. If I were to work with the conditions a little bit, I could probably do better on the left one as well with the ethoxide. But that's a topic for another day. So, how do I get there? All right, so for our mechanism, basically we have a couple things to keep in mind. One is that our halogen needs to be anti to the leaving group. Now, because there's free rotation, I can get that in any of these cases without too much trouble, but I'm going to try and draw it that way anyway, just to make our lives a little simpler. So I'm going to just draw the hydrogen we need on each of the two carbons where the elimination can occur. Anti to the bromine. So in the top case, the less favorable one for ethoxide, it's going to look like this. I'm just going to pull that hydrogen at the same time, form the pi bond, at the same time, displace the bromine. So that is going to give me the pi bond there, and methyl here, and ethyl here. So this methyl is this one. And the ethyl group is the leftover side chain. The other case, all right, for the lower one, I'm going to change colors just so we can see a little bit better. So we're going to have the attack happening to that hydrogen, still anti to the bromine. We're forming the pi bond between those carbons now, and still displacing the bromine as our last step. So if I did that, what I end up with is this. I have the methyl group at the bottom where it was. Here's my new alkene going to the carbon where the leaving group was. And what's left on the carbon where the leaving group was, that carbon is this one, is two methyl groups. So that's all I wanted to see from you mechanism-wise, just that you could follow the electrons to see how this happens. You're getting the impression from the stuff we've done since that exam that mechanisms come up a lot. And they do. And it's important to help you understand why certain reactions happen and how they work. So that's why I wanted to get in the habit of starting to draw them, even when we hadn't seen that many of them.